Hi, my name is Dalpreet Kullar, and this is my final project for parallels. In this project, I implemented and compared the performance of the trapezoidal rule for numerical integration. We did this in three programs in sequential, OpenMP, and MPI-based parallel versions. The function I'm integrating is a Taylor approximation of sine of x, but for the sequential example, I used a simpler function. We used f of x equals x squared over the intervals 0 and 10. We also measured the execution time so we can evaluate the speed up. We mostly did this in our OpenMP and MPI versions. So, what does the sequential version do? We define the function f of x as x squared. I use the trapezoidal rule to estimate the definite integral over 0, 10 with 1 million trapezoids for better precision. The trapezoidal rule works by dividing the interval into n subintervals of width h and summing the function values at each point. This allows each trapezoid area, or we treat each as a trapezoid area under the curve. Let's go over the breakdown of our code here. Here we define the function to integrate. In this case, is f of x equals x squared. Then we have our trapezoidal rule function, which implements the trapezoidal rule. It'll calculate h equals b minus a over n. Starts with half the function values at the endpoints. Then we loop over the intervals and sum up the intermediate function values. In our main, we set the integration bounds a equals 0, b equals 10, and n is 1 million trapezoids. Then we basically calculate the execution time and the results. Let's execute our code here. Make /trap. Here we can see the output shows the estimated integral, the expected analytical result, the absolute error, and the time taken. With 1 million trapezoids, the approximation was very close, and we proved this in our proposal by comparing it to Wolfram Alpha. Let's move on to our MPI version. MPI. Perfect. Here is our MPI code. So now let's look at our MPI version here. This version uses process level parallelism to divide the computation across multiple processes, which is useful when distributing memory systems. What does our MPI code do? In this version, we compute the integral of a Taylor series approximation of sine of x over the interval 0 and pi. The function we integrate here is this, which is x to the power of 3, or x cubed over 6, plus x to the power of 5 over 120 minus x to the power of 7 over 5040 plus x to the power of 9 over 362,880. This interval is split evenly across the MPI processes, which each computing a portion of the integral using the trapezoidal rule. The results are then combined using MPI reduce to produce the final result. Let's go over the code here a little bit. Our trapezoidal function over here, we basically, each process uses the trapezoidal rule to compute its portion of the integral independently. And some other key parts of the code is we have initializing MPI, and we get each process's rank and the total number of processes. And then we get the execution time and the results. Let's run this code and see what we can get. So we simply make it's not // it is MPI run. We'll do this for 4 processes. /trap underscore MPI. Here we can see our result, and we can confirm this on Wolfram Alpha. We put the equation here, and the result we got was 2.0018, and we got very accurate result. The time is 0.07. Let's do this with other processes here. 2, we can see the time goes quicker, or the execution time is quicker. Let's go for more. And speed. As you can see, for our MPI execution times here, we get accurate results for all processes, and for more threads, we are getting faster execution times. Now, let's move on to our OpenMP. Okay. OpenMP. Okay, perfect. So, like the MPI version, we integrate the same Taylor approximation of sine of x over the interval 0 and pi. However, instead of dividing the work among processes, we divide the loop integration among threads using OpenMP. I might have accidentally said threads on the MPI version, but I meant to say processes when we were doing the 1, 2, 4, and 8. Let's go through a little bit of the line by line here. We have our trapezoidal, where we use open set num threads to control how many threads to use. And then we parallelize the loop that sums up the trapezoid values using pragma. This reduction ensures each thread safely contributes to the total sum. Then in our main, the program accepts the number of threads as the command line. For our testing, we did 1, 2, 4, and 8 as I demonstrated for MPI execution. Here, let's give this execution a go here. /trap underscore p. Oh, okay. Here again, our result is fairly accurate compared to our Wolfram Alpha function that we put in. For one thread, it was 0.05. Let's try 2, 0.02. Let's try 4, 0.01. It's getting quicker. And finally, let's try 8, which is also fairly quicker. These results are different, but similar to the ones I have reported into our report here. And we can basically see OpenMP slightly let me bring up the, here we go. Yeah, so OpenMP slightly outperformed MPI in most cases, which could be due to its lower overhead and in shared memory. But both produced highly accurate results, and which the answer was 2. So in conclusion, this project showed how the trapezoidal rule can be parallelized using both MPI and OpenMP, and I learned a lot how to divide workloads, managing synchronization, and the measuring speed-ups pretty much. Overall though, OpenMP was easier to implement for shared memory, while MPI can be considered good for better scaling on distributed systems. Thank you for watching my final project demonstration. My name is Dalpreet, and this was my parallel project. Thank you.